Hi, good morning to everyone. Still got a couple of minutes to go before we start. So if you just bear with us and we'll wait for the start at 11 o'clock UK time. Thank you. Hi, good morning everybody. Thank you for attending. This is a short webinar on developing a basis of safety for powders and dusts. A little bit about the background of the company, just to tell you who we are. We're Sigma-HSE is a group of companies. Our headquarters are in the UK, but we've got presence both in India and the USA, as well as the UK. We bring together our UK, Indian and USA experts to provide our clients with global HSE services and cost-effective engineering solutions. We undertake laboratory testing only in our UK laboratories, though we do have a small test lab in Hyderabad in India as well. And we undertake to BSEN, ASTM, or other internationally recognized standards. You can see we're broken down from consultancy, testing, and training, which is part of today. The technical side, we have highly qualified engineers, scientists, and chemists, experienced professionals, sit on standards committees, some of us. We have experience working with global industries, experience in diverse sectors such as pharma, food, chemicals, oil and gas, utilities, personal healthcare, and it carries on. We can do dust, gas, and vapor, fire and explosion testing in our laboratory in the UK, and we can do some dust testing in our Hyderabad laboratory in India. Along with electrostatics, which is one of our areas of expertise, we can provide consultancy or we can do the testing for it. We have a fully equipped chemical reaction hazards test laboratory here with skilled personnel working in there. And we work under ISO 17025, the only laboratory in the UK that works under that accreditation. Our consultancy team provides a wide range of specialist technical knowledge, such as areas of fire and explosion. In Europe, it's ATEX. In the UK, it's DESIR. We can do electrostatic measurements and problem solving, and we also cover areas such as PHA, QRA, hazard, HAZOPS, etc. And we have skilled people that can assist in the area of functional safety for electrical equipment. It's LOPA, layers of protection analysis, and SIL. And we have training workshops, both public, in-house, and things like webinars. So what I'm going to talk about today is the basis of safety. As you can see here, the company didn't have a basis of safety or a robust one, because if they did, this wouldn't happen. And the idea of this talk is for people to understand that it can happen to you. unbelievably, as you may think, but yes, it can happen to you. It just doesn't happen to everybody else. So what is the basis of safety? Well, it's a combination of measures they rely upon to ensure safety, and they highlight the aspects of design and operation which are safety critical. Overall safety strategy can be applied to any of the following. It can be to do with your equipment on site, the various processes that you operate, the areas to which you're working, and the work instructions that you issue, such as SOPs, etc., or manufacturer's documentation for equipment. In order to build any basis of safety, it is necessary to have information available. And these would include things like equipment specifications, operating procedures. Hazardous area classification is very important because you need to know how frequently the flammable or hazardous material is present for. Maintenance procedures. Do you have these in place? Do you have permit to work systems in place? Management of change. What materials are being handled? Do these change over a period of time? And if they do, have you adjusted your basis of safety to suit? Flammability data, such as minimum ignition energy, layer ignition temperature, minimum ignition temperature, the dust constant KST, Pmax, and the list goes on. The data you need for any basis of safety has to be for that basis of safety. Always remember, with a world shortage of materials, many companies are turning to new suppliers. This means that some of the material properties may change, and therefore, we always advise you retest these products. So we're going to build an effective basis of safety. First thing we put in is, what equipment are we using? Is it designed for the job? Procedures. Do we have standard operating procedures in for people working with this equipment? Are they fully trained in how to use it? Do they understand legislation such as DESIR and ATEX? Have they received formal training at all? Deviation from normal operating conditions or processes. Friday afternoon, let's increase the temperature. Let's increase the flow rate. Let's increase the amount of material we put into the operation because we need to get it out before close of shift on Friday. Will this have a detrimental effect on the basis of safety that you've put together? Human factors. This is a debatable issue. Humans sometimes are extremely good. Someone working on a piece of equipment for a good many years will sense something's wrong. He will smell something, hear something, or see something which he's not happy with, and he will shut this process down. On the other hand, humans can do the most ridiculous things ever. And not only can they do them, they can actually repeat the action after they found out that it didn't work the first time. So you must look at human factors to decide if things can go wrong, and if it does, how bad is the effect? Material properties. Are they corrosive, toxic, for instance? Do they self-heat? Acidic, alkaline? These are the things that you may have to look at because it's no good putting explosion protection in place with venting if you've got a highly toxic material. And also flammability. You'll need flammability data to be able to prove your basis of safety. Risk level and tolerance. For instance, You look at a risk and you say, we're happy to take moderate risk on this because we're outside in a greenfield site. If explosion vents go off, we're not too worried. On the other hand, if you're in a built-up area with housing close by, you really don't want vents going off regularly. It scares the locals. And you may have many more things, depending on your operation and processes, that you may want to add to form your basis of safety. And when we took it, powders and dusts, there are normally three types of safety for fire and explosion risks. We have explosion prevention, which means achieved by avoiding the flammable atmosphere. The most common way is to remove the material, often not possible because it's part of your process, or remove the oxygen. If you do that, then you need the LOC. But again, working with materials like nitrogen, for instance, can be extremely hazardous. And a lot of people have died by asphyxiation by not having a complete knowledge of working with nitrogen. Avoidance of ignition sources. What ignition sources do you have? Can they become active? And can they become effective? So you need to avoid sufficient energy to ignite and cause an explosion. Explosion protection. Reduce the damage done to plant, employees by explosions. This is a common method of safety. It has its advantages, it has its disadvantages, which we'll talk about later in the talk. So what are the conditions for a dust explosion? Well, the dust must be flammable, combustible, and airborne to form a cloud of dust. The concentration must be within explosible limits. This means above the minimum explosive concentration. Notice with dust there is no upper limit, unlike gases and vapors, which has an LEL and a UEL. But be careful with the MEC because slugs of material may come through a system which rise above the MEC. You need to look at the particle size distribution. Is it capable of propagating flame? Normally we look at 500 micron and say below that, this is a risk. And does the atmosphere or the oxygen available support combustion? It must have a sufficiently energetic ignition source. There's no problem with having an ignition source as long as it's not an effective one. So, fuel, oxidant, ignition source, the three things you need for a fire, the fire triangle. But then we mix the flammable materials such as the dust in with the air to form a dust cloud. And then we confine it. And that's when the explosion can occur. So why is flammability testing important? Well, it's required to understand the explosive properties of your materials. It's required to understand the sensitivity of materials to potential ignition sources. It helps you determine whether you can stay outside the flammable limits. And as of 2021, it's actually a legal requirement nowadays for dust flammability data to be put onto safety data sheets. This is rarely the case, but within Europe, it is part of the safety system now. And we look at testing, and we can split it into three sections. We need data for explosion prevention, data for avoidance of ignition sources, and data for explosion protection. So in the EU, the safety data sheets came in on the 1st of January 2021. And Annex 2 of REACH, regulations for chemicals, has been amended concerning the compilation of safety data sheets to cover this. So therefore, it's a legal requirement to include data such as minimum ignition energy, layer ignition temperature, minimum ignition temperature, Pmax, KST, lower and upper explosion limits. As I said before, it will only be the MEC for dusts. For gases and vapors, flash point, auto ignition temperature have had to be on safety data sheets for many years. So what types of flammability data would we require for powders and dusts? Minimum ignition energy. This looks electrostatic hazards and the risk of ignition from mechanical equipment. Note here that the MIE done with pure capacitance will look only at electrostatic issues. You must have it done with an inductor in the system for mechanical sparks. In Europe, both of these test methods are acceptable. But when you have your data on your sheets, make sure it's done with the correct MIE. If you look with the inductance in, often that is much lower value than without. Minimum ignition temperature considers hot surfaces, ignition of a dust cloud. So this would be used for electrical equipment, for instance. Layer ignition temperature considers hot surfaces for powder layers. The maximum pressure evolved during an explosion, the dust constant, and the dust class are used for explosion protection. Minimum explosive concentration considers the flammable range. Limiting oxygen concentration considers inerting. Burning behavior looks at the risk of fire spreading rapidly with layers of powder. The resistivity looks at electrostatic issues and equipment specifications for zoned areas. So you need to know whether the material is conducting or insulating and whether it can hold electrostatic charge for long periods of time. And to complement this, we have charge relaxation time, which looks at the same properties but allows you to have an idea how long it can hold its charge for. And at the end, there's thermal stability. Thermal stability is often ignored by people, but if you're storing material at high temperature coming out of dryers into silos, what is the risk of ignition from thermal decomposition? When you're drying, what are the risks with a spray dryer, fluid bed dryer, a tray dryer, for instance? So we'll look at explosion prevention now. Well, with all basis of safety, we'll start off with a Group A-B classification test. This determines whether a material will form a flammable atmosphere when dispersed in air, therefore subject to the regulations set out, such as DESIR and ATEX. So it could be combustible, that is Group A. That means it's flammable or explosive as a dust cloud, in which case you're covered by regulations, and then you have to look at developing a secure basis of safety. And then non-combustible, which is Group B, which means that it's non-flammable or explosive as a dust cloud. So you're not covered by the regulations. But always remember, a non-combustible dust may still undergo self-heating and create a fire situation. . So looking at explosion prevention, Looking at the limiting oxygen concentration is the minimum allowable concentration of oxygen in a mixture of dispersed combustible dust with air and inert gas in which an explosion will not occur. So this means it's the highest level of oxygen which will not support combustion. It's generally higher than for gases with dusts, but sometimes it can be quite low. Typical values are anywhere 10 to 15%, and the values you get are used using nitrogen as the inert gas. It's conducted to BSEN 14034-4 from 2004. Typical examples: rye flour 13, organic pigments 12, methyl cellulose 10, beta naphthol 9.5, and now we start coming lower: sulfur 7, paraformaldehyde 6, and materials like aluminium 5. And I've actually found active pharmaceutical ingredients ignite at 4%. So the other side of minimum explosion prevention is the minimum explosive concentration. Now, the MEC is the minimum quantity of dust dispersed in air that is required to form a flammable atmosphere. The example on the other side shows 40 grams per cubic meter of coal dust, which means you struggle to see a 25-watt light bulb at a distance of 2 meters. So it's a pretty dense concentration of dust. Sometimes the MEC is referred to as the lower flammable limit. And again, 14034 is the test standard, but this time section 3. A lot of people like to have a look at, can we get away with avoidance of ignition sources? Can we ascertain if we have ignition sources present, and will they become effective to ignite the cloud? Things like radio frequency electromagnetic radiation, visible and high frequency electromagnetic radiation, lightning, ionizing radiation, static electricity, stray electric currents within the installations, exothermic reactions, and spontaneous combustion, electrical apparatus, adiabatic compression and shock waves, mechanical friction and thermite sparks, ultrasonic sound waves, flame smoking and hot work, and hot surfaces. I've highlighted in yellow the most common ones that you'll find when you're looking at avoidance of ignition sources that require test data. If you look at electrical apparatus, this is obviously a potential ignition source. And for this, you would follow directions and regulations for ensuring the correct electrical equipment is installed in the hazardous area for the material they're using. So test data will help in the selection of electrical apparatus as well. So what is the minimum ignition energy? It's the lowest spark energy that can ignite the optimum mixture of fuel when dispersed in air. As I explained to you before, there are two types: capacitive discharge, which looks at electrostatic discharges, people, isolated conductors, etc., and inductive discharge, which takes into consideration mechanical sparking. Make sure you have the right one for the right application. And often when you see data on MSDSs, etc., firstly, it's generic data, which is probably years and years old, up to 50 years old. And secondly, it could easily have been done with inductive discharge, which may give you a much lower value. We've had materials tested with capacitive is 100 millijoules, with inductive is 10 millijoules. So ensure you have the right data to be able to analyze the ignition sensitivity. Any ignition source with an energy greater than the material's MIE is capable of providing ignition to the flammable atmosphere. And it's conducted to 13821 2002. And the BSEN ISO standard, which is nowadays accepted probably worldwide, is 80,079-20-2. So what types of value would you expect? Well, starch, 100 to 300 millijoules. Be careful here, because there are hundreds of varieties of starch. And I've come and found out that some starches are 5 to 10 millijoules. So even though you've got a generic material, starch, check it out to make sure that it is correct, the data on the MSDS. Glass reinforced plastic dust can be 30 to 100 millijoules. Sugar, 10 to 30 millijoules, but again, depends if it's things like icing sugar, which can be extremely low, 5 to 10 millijoules. Aluminium, which will vary considerably depending on the particle size. And this can range from 3 millijoules for very fine aluminium, above 10 millijoules to even 150 millijoules for quite coarse material. Active pharmaceutical ingredients can be as low as 1 to 3 millijoules, which means they can be as ignition sensitive as gases and vapors. If we look at the minimum ignition temperature, this is the lowest surface temperature that it can ignite the optimum mixture of fuel, dust, that is, when dispersed in air. You can see here on the right a flame coming out as the dust is dispersed through the top. It forms a dust cloud inside, hits the hot surface, and there you see the flame, resultant flame coming out. That is an ignition. The MIT is often referred to as the auto ignition temperature for dust. It's used to calculate the maximum permitted surface temperature of equipment. And the temperature range could vary between 200 to 700 degrees. And again here you can see the standard we test to is 50281-2-1, or the ISO standard, same again, 80,079-22. Complementing the MIT is the layer ignition temperature. This is the lowest surface temperature that can ignite a 5 millimeter layer of material. In the United States, they changed their standards, the ASTM standards, and we hoped they'd follow suit and keep to 5 millimeter, but they didn't. They made it 10 millimeter. So if you have data from America, it will give you a lower LIT. As the layer gets thicker, so the temperature decreases. The LIT is used with the MIT to calculate the maximum surface temperature of equipment. The range in this case is 200 to 400 plus degrees. 50281-2-1 again, and we're back to 80,079-22. So what are the most common ignition sources you would take into consideration here? Electrostatics, well, the risk is high due to some dusts having very low MIE values, down to less than 1 millijoule with active pharmaceutical ingredients, which are similar to gases and vapors. Flames and hot work. the risk is high again, and ignition would depend on the minimum ignition temperature of the dust, in other words, the dust cloud that could occur with flames and hot work present. Hot surfaces, they're there all across manufacturing processes. One of the most common would be electrical motors. The risk is moderate, as many values of MIT and LIT are quite high. Although be careful, some materials do have much lower values, sulfur in particular, or sulfur salts. Electrical sparks. All electrical equipment must be suitable for use for any given flammable dust. And in the UK and the EU, the equipment must be ATEX certified for use in a zoned area. And we have mechanical sparks. The risk of ignition is high from these when there are very low values for MIE combined with MIT. And mechanical sparks as well, if they ignite something, can cause an explosion or burning embers, which could transmit throughout your process. A good idea here about dust explosion ignition risk. Mechanical's the highest there, and overheating, again, you see the two high ones. Open flames, you need to control those, permit to work systems, etc., hot work permits. Electrostatic ignition, quite high. Welding, again, must be controlled with an industrial environment. Electrical is quite low because it used to be called Electrical Equipment Hazardous Area Classification. So the system has been around for a good many years. And then we had other, which means someone is not capable of determining what caused the explosion risk. This often means that the person who did the assessment was not capable of doing it correctly. So always try to get people who are experts in the field to come and have a look at it, any incidents. There are about 40 dust explosions annually, and they result in injury and loss of life. Often plant repair, compensation claims, manufacturing reputation is destroyed. Business interruption happens and you lose loss of market. And of course, insurance companies, they're not too keen on insuring people that blow up their plant. So hot surfaces and temperature classes. The maximum surface temperature of equipment has to be lower than the LIT or MIT of the worst case material being used. For gases and vapors, temperature classes of equipment exist, but dusts are given as a maximum temperature so that equipment can be properly specified for their application. So for gases and vapors, you'll see T1, T2, down to T6. If you look at the equipment, you will see for dust, it's an actual maximum temperature. For dust, the limit temperature of equipment is likely at 2/3 the value you obtained in the MIT test, or if there's layers on top, then it's the LIT minus 75 degrees. Usually because the LIT is over a long period of time, up to 30 minutes, it ends up being lower than the MIT for dusts. But very occasionally, we get it the other way around. So, flame smoking and hot work. These should be controlled, as I said before, by permit to work systems. Make staff aware of hazards to avoid likelihood of common ignition source problems. Make sure if you are going to work, you remove the flammable material out of the area you're working in and try to do it in a workshop. Smoking used to be a problem, but today people ban it on the sites and they make it only in designated areas. The same applies for vaping. Vapes are not ATEX compliant and should not be taken into hazardous areas. So control all access to hazardous areas. So management of change, permit to work systems, hot work systems should be in place wherever you have a hazardous area. Electrical equipment for dusts. Electrical apparatus in hazardous areas must be suitable for use in the area that you've been designated, depending on the following. Things like the MIT and LIT to ensure the surface temperature is correct. Zonal classification for the area in which it is to be located is at zone 20, dust is there all the time, 21 normally during manufacturing, 22 just occasionally. Do you have the ingress protection rating correct? And the type of powder, is it conducting or insulating? These can have a large effect on electrical equipment. If it's insulating, then that can build up charge. If it's conducting, then you could get a short occur. And electrical equipment must be installed and maintained by competent personnel. In the EU, these are COMPEX certified people. If you look at the typical label you'll see for dust, the European conformity marking, the EX showing that this explosion protected by a notified body, it's Group 2, Category 2, suitable for dusts. EX means explosion protection, and the type of protection is TB. The dust category is 3C. The temperature rating is 80 degrees, and the dB is the equipment category under ATEX. Ignition by mechanical equipment. This can be activated by either friction, grinding, or impact sparks. And also, mechanical can have hot surfaces. Flames and hot gases should also be considered. As we've shown before, if we combine the minimum ignition energy with inductance and the MIT, we can determine whether friction, grinding, or impact sparks are a cause for concern. Do they have sufficient energy to ignite your particular dust cloud? If fitted before 2003, then all equipment located in hazardous areas should undergo a non-electrical equipment ignition risk assessment, a NERA. After 2003, they have to be compliant under the ATEX directives. So how do you reduce ignition by mechanical sparking? Reduce the energy less than the MIE of the dust. Quite often not possible, but good maintenance should ensure you don't get sparking from equipment. Slow down the rotating equipment, often difficult. If you're manufacturing, you want as much material through as possible. Put methods to remove tramp metal or foreign bodies in, filters, filter screens, magnets, etc. Put your bearings and seals on the outside of the equipment so they don't get hot on the inside. Control the material feed rates. Again, pressures and industry tell you that you want to get as much material as possible through. So it's very difficult to get people to sign on to this one. Have temperature monitoring on your equipment to see if the bearings are overheating or to see if you've got striking metal inside the equipment. Regular maintenance, inspections, and lubrication are very important, and good housekeeping. Keep the areas clean around the equipment and on the equipment. So a non-electrical ignition risk assessment have to take in certain considerations with this when you do the risk assessment. You have to look at the CE markings, the IP rating. ingress protection, speed of moving parts, whether the material, whether the equipment is suitably earthed, doesn't become an isolated conductor. Look at the materials of construction. Are they brass, aluminium, stainless steel? Look at temperature rises and the ratings for the temperature. Can they produce sparks or emissions of sparks? So look at materials to avoid electrostatic discharges such as insulators or plastics. Avoid frictional contact between steel and certain alloys. Minimization of leakage of dangerous substances from the equipment. Dust layer impact on the temperature rise of the equipment. What SOPs do you have in place? Are you following the manufacturer's operating procedures? Are your maintenance activities in place correctly? What type of environment is the equipment in for temperature rise? Is it in a hot area? Are you producing next door to dryers in a closed environment? Do you have systems in place where you have spark detectors? Can you mitigate effects in systems? Are you following manufacturer's instructions? Overall, do you have the correct installation? Typical nearer example here, rotating blades, hot surfaces, the motor body, bearings, mechanical sparking, contact between the baffles and the casings, friction, impact and grinding, sparks that could occur, isolated conductors, electrostatics, and outside you've got a gearbox. It could overheat. People talk about static electricity. It is a specialized subject, and we do deal with it a lot here in Sigma. It's the only ignition source mentioned explicitly in the Dangerous Substances Explosive Atmospheres Regulations and the Atmosphere Explosive Regulations 153 as one of the ignition sources to be controlled. Static electricity is generated wherever movement takes place, and it's often intrinsic to the intended process, and it is a specialized subject. So how do you assess static hazards? Do you have a flammable atmosphere? Can you generate charge? Does that charge accumulate? What sort of energy can be provided? And what is the discharge mechanism if you have a spark? Typical discharge mechanisms, corona, come from sharp points of earth conductors near a highly charged object. Very minimal, they're non-incentive unless they develop into a spark. But again, you have to say they're very low energy, probably 2 millijoules. Brush discharges, charged insulator discharged to earth, such as plastic sheets, 3 to 4 millijoules. These will ignite gases and vapors where the energy is greater than the MIE of the gas or vapor, but they will not ignite dust, even though a dust may have an MIE of 1 or 2 millijoules. Spark discharge is probably the most common one from people, etc., or charged isolated conductors. E over half CV squared, 0 to 100 millijoules. If it is a large object which is isolated, they could rise to 150 millijoules. They will ignite gases, vapors, dusts, and mists, where the energy is greater than the MIE. Cone discharges, highly charged insulating powder filled into metal earth silos. So you've got an insulating material kept in an earthed metal silo. So short, fat ones are worse than tall, thin ones, basically. And this is where you reverse the trend. Large particle sizes produce a higher energy discharge. So granules will charge up higher and produce a larger energy. Combine that with fine dust above, and you've got a recipe for failure. These can be up to 150 millijoules, can ignite gases, vapors, dust, mists, again where the energy is greater than MIE. And the worst one is the propagating brush discharge. Two surfaces of high resistivity material oppositely charged. Basically, if you have a thin deposit of insulating material on a metal substrate, it forms an electrolytic capacitor. And the discharges can be up to a joule. And obviously these will ignite just about everything that you come in contact with. And be wary, they can do serious damage to human beings as well. So summary of avoidance of ignition sources. Consider all types of ignition sources. I showed you the 13 previously, but concentrate on the 5 most important. Hot surfaces, flames and hot work, electrostatic, mechanical and electrical. Perform hazardous area classification so you know the animal you're dealing with. Is material there all the time, during manufacturing, or very little? Ensure all equipment is suitable for use in the zone. So, if it's a zone 20 area, it will have a higher level of safety than a zone 22 area. Consider more detailed assessments looking at electrostatic discharges, electrical inspections and fittings, and mechanical problems and hazards. Always remember, you may have the correct electrical equipment installed, but is it installed correctly? So make sure that the people who are installing it and maintaining it have been suitably trained. And in the UK, we have the compact scheme for that. Control all naked flames and hot work by permit systems. Obtain suitable flammability data. You cannot determine how a material ignites unless you have the flammability data. Understand if potential sources of ignition, can they become active and effective? And write everything down in a basis of safety report. The final one we're looking at is explosion protection. Imperial and Sugar didn't have a basis of safety in 2008, 14 deaths, 38 injuries, 14 life-threatening burns, explosion fueled by accumulation of sugar dust and complete propagation throughout the manufacturing processes and the associated buildings. So you get the data from the 20-litre sphere, the maximum explosion pressure evolved. The dust constant comes from the rate of pressure rise. Explosion severity data is required for systems like venting, suppression, or containment, if these are your proposed basis of safety. Conducted under 14034, Section 1. Typical values here for dust: ST0, ST1, ST2, and ST3. ST means Staub for dust. KST, constant, dust constant, Staub constant. So 0 is no explosion. ST1 0 to 200, notice that says weak explosion, but Imperial in Sugar was a weak explosion. ST2, 200 to 300, these are a strong explosion, polymethyl acrylate, wood flour. ST3s greater than 300, no upper limit, very strong explosion. Anthraquinone, aluminium, magnesium, metals. And today you can add in aluminium lithium hydride used in batteries, and this reached 1,200 KST. So mitigation of risks. If risks cannot be eliminated or controlled, the detrimental effects must be mitigated. Always try and reduce the number of employees that are exposed in hazardous situations. Certainly avoid the propagation of fires and explosions. You can have explosion relief arrangements, explosion suppression, or you can use containment. Personal protection equipment, so static dissipative gloves, clothing, and shoes, combined with static dissipative flooring. If several dangerous substances, look at the worst case. Consider safe handling, storage, and transport of dangerous substances, and always look at waste. It is the same material you're producing. An explosion in a closed vessel. So you have the rate of pressure rise coming up, dP, rate of pressure over time, and the maximum pressure evolved. In a closed vessel, the pressure will increase, and any protection system must be able to cope with the expansion and/or pressure increase within this very short time interval. So dPTT is measured in the 20-liter sphere, and then we convert over to an explosion in a 1 cubic meter vessel, which gives you the dust constant. dPT will change depending on the vessel size, KST will not. If you consider containment, isolate pieces of equipment where explosions could occur. All isolated plant to withstand the overpressure of the explosion. No release of combustion products or toxics, no requirement position of safe areas. On the other hand, the equipment is expensive to build and maintain, requires pressure testing and associated documentation, and the equipment is very heavy. Maintenance people have to understand you have 27 bolts, let's say, round a flange for a reason. They all have to be put back. So, all parts of the plant made strong, including pipes, ducts, flanges, covers, must withstand the maximum pressure that is expected and then maintain the strength over the lifetime of the plant. They must be explosion pressure resistant or explosion shock resistant. Shock resistant, you will get some deformation. Strong plant is expensive to build and can be difficult to operate and maintain. People have to understand it is a pressure vessel. One of the most common ways of looking at explosion protection is venting. So you protect plant and personnel from the effects of an explosion. You get a controlled release of pressure via weak sections that open. Vent sizing is determined via the KST value and Pmax data taken from the 20-liter sphere testing. Positives, it gives the ability to control the release location. It is a passive protection system, can be retrofitted to weak equipment. Side effects is it produces combustion products and overpressure, which are released out into the atmosphere. Non-flameless systems can lead to explosion propagation. So its advantages can be designed in-house. It's relatively cheap for the vent itself, needs very little maintenance, has a very wide range of applications. Disadvantages, which you have to look at as well, is material is released. Therefore, if you've got toxic or corrosive, venting is not the best way to go. Must discharge outside to a safe area. This restricts the siting of the item within the plant. They must be put on an outside wall. And large safe areas outside are required so people don't get injured when the explosion vents out. And then you have flameless venting, which has occurred over the last few years. These are special devices attached to the explosion vent, can stop the flame while allowing venting. Items such as Q-roar, flame quench. The efficiency is reduced compared to a bursting disc because basically this is a flame protection device. And there's, as you can see with the picture there, small holes allow the pressure and the gases to come out, but the flame will not propagate through the holes. They need to be type tested. So, flames prevented from exiting the vent. But beware, high pressure and smoke can still fill the workplace. So look at the picture on the right and you'll see it's located within a building. If an explosion comes out through this, then the workplace will be filled with smoke and very high pressure gases around the area of the vent. So it must be sited in a restricted area. It requires regular maintenance. So people have to come in and check it to make sure it's still suitable for use over time. And make sure it's suitable for your material. So toxic gas can come out through these things. Caramelization. Look at sugar, it caramelizes. Those small holes over a period of time get closed up by caramelized sugar, blocking the vent, and then your equipment will explode. You can put in explosion relief doors. Doesn't require a replacement after an explosion. Easy to maintain and cheap to fit. You can see them there. They are an option. Problem is you have to prevent the door closing too quickly after the explosion, and I'll show you why. They can weather badly because they're never maintained. They should always be robust, and this should not be compromised by putting things on top of them to keep them shut, letting them rust so the hinges don't open, get them corrode so they have holes in them. They have to be maintained and looked after carefully. And this is often the failure with them, poor maintenance. This is what happens if the door closes too quick. If the vent opening closes after the explosion is vented, the hot combustion gases will cool down and create a negative pressure. If you look at that, if you put a plastic lidded container in a microwave, heat it up, switch the microwave off and leave it, you can't get the lid off the container because as the materials cool down, they cause a vacuum inside. VDI 3673 does provide information on the sizes of vacuum breakers for these cases. Flame propagation. This is what the big failure in imperial sugar. Most of the fuel air mixture will be expelled from the vent and burn outside the vessel. As I said to you before, a large safe area must be allowed. For dust, the length of the flame is 8 to 10 meters times V to a third. Therefore, if you make the vessel 1 cubic meter, you've got a potential 10-meter length of flame coming out of this vessel that needs to be left clear. And this is the problem I come up against, seeing explosion vents in areas where they're facing buildings, facing windows, over doorways, facing each other. They have to be sited correctly. The length is never more than 60 meters. For gases, it's only 5 times. The width, on the other hand, is difficult to predict, but the EN standards has a formula for dust. Vent problems, as you can see, badly maintained vent that is not going to operate correctly. If the vessel explodes, then it will not release the pressure out fast enough and the vessel will buckle and break. Materials on top, because they leak water down into them, again, these will become flying missiles. The other way is to look at suppression systems, extinguish the explosions in their early stages, and inject pressurized suppression agents inside. There are no external effects that are suitable for toxics, and they rely on effective explosion detection and their highly specialized design. So advantages: don't release material, no restrictions on where the plant is located in that case, no flame propagation, and isolation devices in a well-designed system. Disadvantages: pretty expensive, need very regular maintenance, only works when it's operational. After activation, you have to recharge the bottles, and of course, there's a total loss of product. Typical examples here on a fluid bed dryer and a dust collector. So isolation, necessary to prevent pressure piling effects and flame jet ignition. Without isolation, the explosion in secondary vessels could be more severe than what the design criteria is. And obviously there's a risk of secondary explosion. If an explosion increases the pressure in the next area by 1 bar, then if it was 7 bar, then it becomes 14. And so it goes on. The pressure piling effects. Typical isolating equipment: rotary valves, fast closing valves. Always remember, rotary valves will stop an explosion, but they will not stop fire propagating around them. So a summary for explosion protection: determine the flammability characteristics of the materials, review the SDS to see if materials have hazardous properties, i.e. toxic, corrosive. Look at the hazardous area classification so you can identify equipment locations. Venting and suppression systems need to be designed and installed, as should fire protection. For containment, the vessel needs to be certified for use at the pressures, and maintenance people need to be trained for pressure vessels. Location may be a problem for venting. Isolation must be in place. Assess special procedures, hot work permits, management of change. Personnel and working in these areas have to be trained and why they're there. So, overview: a combination of measures relied upon to ensure safety, highlight the aspects of design and operation, and consider many items: equipment, procedures, deviations, human factors, material properties, level of acceptable risk. For fires and explosions, explosion prevention, avoidance of ignition sources, and explosion protection. So, quick overview here. For explosion prevention, you can't change the flammable material, so it's normally oxygen is inerting, or work outside the flammable ranges for gases and vapors. Not really possible for dust, as powders are non-homogeneous. Sorry, I went backwards instead of forwards there. Avoidance of ignition sources. All ignition sources need to be considered. Most common ignition sources: hot surfaces, naked flames, electrical, electrostatic discharges, and mechanical sparking. So look at material properties, things like MIE. For material properties, you may need further electrostatic data, resistivity, charge relactation, minimum ignition temperature, layer ignition temperature, 20 liter for explosion protection, LOC for explosion prevention. Summary of basis of safety: always do hazardous area classification, always consider potential ignition sources. If required, do an electrostatic audit to make sure the MIE, especially if the MIE is low, and if there's dust or gases and vapors present. Always check out equipment specifications and their suitability. Look at operating procedures, do risk assessments, and always take into consideration the properties of the material. Assess the process to look at manufacturing hazards, charging and discharge, mixing, etc. Your process maintenance procedures with permits. Look at the personnel working to make sure they're trained and determine what basis of safety you can actually apply. Well, that's it. I hope you all found that useful. Thank you very much for attending, and I hope you appear at our next presentation. Many thanks.